Edexcel Decision 1, Graphs and Networks 4, the Travelling Salesperson Problem. Finding an upper bound, nearest neighbour. So we want to find an upper bound solution to the travelling salesperson problem in a methodical way. We'll be looking at two methods. The first was the minimum spanning tree method that we looked at in the previous video. This involved selecting shortcuts, but it was very time consuming and difficult, particularly if there was a large network involved. The second method is a nearest neighbour algorithm, and this method is often used because it's easily programmable. This method is used to find a valid solution, which is not necessarily optimal. So for the nearest neighbour algorithm, we need to choose any vertex as a starting point. We then select the nearest vertex to the one we have just chosen, as long as it's not already selected. We then repeat step 2 until all vertices have been selected. Once all vertices have been selected, we join the last vertex to the first vertex to create a cycle. Okay, so we're going to use the nearest neighbour algorithm on this network. You might notice that this network is K5, the complete graph with 5 nodes, as all nodes are directly connected to every other node. So we're going to use the algorithm starting at node A first of all. And if you look at node A, we can see that B is 8 away, C is 13, D is 11, and E is 9. So from A, we go to its nearest neighbour, which is B. So B. So then we look at B. B's nearest neighbour is E. So we go B to E, because it has a weight of 7. So now we're at E. We need to go to a nearest neighbour, and our nearest neighbour is B, but that's already been taken. So D is our next one, and as that hasn't, we can connect E to D. And I'm going to finish writing the tour here. So A, B, E, D. So now we're at D. We want to look for its nearest neighbour. So E is nearest, but we've already selected E. Then B is our next closest, but B has already been used. A is then our next one, but A is also already connected, so we must go to C. So from D, we go up to C, as C hasn't already been included. Now, as we can see, all nodes have been included, so C was the last one we chose, so then we just connect it to the first one. So we go back to A. So next we're going to use a nearest neighbour algorithm starting at B to see if we get a different result. So if we start at B, we can see that our nearest neighbour is E. So we go from B to E. So our tour is B to E. Then at E, our nearest neighbour that hasn't already been included is D. So B, E, D. We go across to D. Then at D, our nearest neighbour is E, but E has already been used. Then B, but B again has already been used. So next one is A. So we go over to A. So now we're at A. Our nearest neighbour that hasn't already been included is C. So we go across to C. And then as C was the last one we've included, we go down to, up to the start, so we go back to B. And we join it back up. So those are our two tours that we get from using A as our starting point and B as our starting point. And the total length of those tours are 50 starting at A and 48 starting at B. Okay, so this is our nearest neighbour algorithm. And what we must always do, unless we're told otherwise, is we must repeat this algorithm for different starting vertices. So we did just repeat it for vertex A and vertex B, but there was still C, D and E that we would need to look at. Because what we want to do is find the least upper bound. So out of the two we just found, we knew that the tour starting at A had a length of 50, and the tour starting at B had a length of 48. So far, the tour starting at B would be our least upper bound, but we'd want to check nodes C, D and E first. So if we were to repeat this for all the 5 starting nodes, we would get the results as follows. So it would be worth at this stage pausing the video and trying for yourself the nearest neighbour algorithm starting at C, then D, then E, and see if you can get the same totals and same TORs as written in this table. So in our network of 5 nodes, we will find at most 5 Hamiltonian cycles. Remember, a Hamiltonian cycle is a cycle that starts and ends at the same vertex and visits every vertex exactly once. So the nearest neighbour algorithm will enable us to find at most 5 of these cycles, and in fact some of these could be the same. So if we look at the table, we can see that A is A, B, E, D, C, A, and D is D, E, B, A, C, D. And if you look closely, A and D are the reverse of each other, but at different starting points. Now, the different starting points doesn't matter, it's just shuffled along, so you can see that this is the reverse of this. So A and D are the same, a Hamiltonian cycle. There are 2 more that are the same. So we've got B here, is B, E, D, A, C, B. And if we look at C, it's the same cycle, just starting in a different place. It's just been shuffled along. So B and C are also the same cycle. So it's important to note that trying to look for Hamiltonian cycles and trying to find an upper bound using the nearest neighbour algorithm are 2 different questions. Don't get confused between the 2, and don't use a nearest neighbour algorithm at every node to check as a way of checking every possible Hamiltonian cycle, as this doesn't work. Remember that in a complete network of 5 nodes, we will have 5 minus 1 over 2, that's 12 different Hamiltonian cycles. And in the previous example, the nearest neighbour algorithm just found 3 of these. Okay, so what can we conclude about the solution to the travelling salesperson problem for this network based on our results? Well, if we remember in the table, starting at node A gave us a tour length of 50, B gave us a tour length of 48, C a tour length of 48, D a tour length of 50, and E a tour length of 55. So if the length of the optimal tour is T, then we conclude for this network that T must be less than or equal to 48. So our least upper bound, according to the nearest neighbour algorithm, is 48. So our next session will be finding a lower bound.